Hey everyone, and welcome back to day 8 of our 90 Days Piping Design Engineering series. I am Lopamudra Satpathy, your host and piping design consultant. Today we are diving into a topic that is fundamental to everything we do in piping: why codes and standards matter. Yeah, you have heard me and many others talk about various codes like ASME 31.3 for process piping, ASME 31.1 for power piping, or even extensive requirements for nuclear facilities. But do you ever think, why are these documents so absolutely critical? Today we are going to break it down into three core pillars that underpin all our work. Think of safety not just a checkbox, but as our non-negotiable vow. In a world where piping systems pulse high pressure, high temperature and hazardous fluids, the margin for error is zero. These codes are more than just a list of don'ts. They are the battle-tested blueprints and survival protocols spanning material science and rigorous testing, designed to stand between a routine operation and a catastrophic failure. So we design by the book so that we can protect the lives behind the walls. Beyond our professional ethics lies the ironclad hand of the law. So courts are not just good advice, they are the legal framework of our industry. Yes, I'm talking about our second pillar, legality. When governments and regulatory bodies adopt these standards, they transform technical guidelines into mandatory law. So, stepping outside these boundaries is not just a design flaw, it is a legal gamble that can end in crippling fines, immediate project seizure, and even criminal charges. So, in our world, compliance is the only permit to practice. Let us go to the third pillar, consistency. Do you ever think why standards are the universal language? Standards are the language which allows an engineer in one corner of the globe to speak clearly to a manufacturer in the another. So imagine the chaos of a world where every bolt and flange was a custom invention. Global industry would grind to a halt. By adhering to standardized codes, we ensure a component forged in China, a wall cast in India, and a pipe extruded in the Germany fit together with mathematical precision. So this consistency is the engine of global procurement and the bridge to seamless worldwide collaboration. So understanding these three pillars is not just passing an exam. It is about building reliable, safe and efficient piping system that stand the test of time. So stick around because we are going to dive deep into each of these with real world example. Let us get started. Let us kick things off with the most critical reason, safety. Imagine a high pressure steam line failing or a flammable chemical leaking in a refinery. So what's the consequences? The consequences can be catastrophic. It might be loss of life, several injuries, environmental damage, and massive financial losses. So codes and standards are essentially battle-tested rule books written by experts to prevent such failures. They dictate minimum requirements for material selection, wall thickness calculation, joint design, welding procedures, pressure testing, and even support spacing. Do you think why? Because every single one of these factors, if not properly controlled, can lead to a hazardous situation. Okay, Let us think about a real-world process piping example. In a chemical plant, you might have lines carrying highly corrosive acids or superheated stream. ASME 31.3 process piping provides detailed guidelines. For instance, it specifies material requirement for a corrosive service, minimum design temperature, and pressure calculation. If you ignore these, you risk a brittle fracture, stress corrosion cracking, or even rupture under operating conditions. So a small oversight in selecting a gasket material not specified by the code could lead a leak of toxic fumes, endangering workers and the public. To understand why we follow codes like ASME 31.3 and API 521, we have to look at what happens when safety standards are bypassed. The Bhopal disaster in 1984. Yes, it is the most sobering lesson in industrial history. For us as piping engineers or designers, it was not just an accident. It was a systematic failure of piping integrity and safety instrumentation. Let us look at the technical reality. Water accidentally entered a storage tank containing 42 tons of methyl isocyanate (MIC). This triggered a violent exothermic reaction. In a code-compliant plant, multiple layers of protection should have stopped the gas from reaching the atmosphere. But look at what happened. The vent gas scrubber. This was supposed to neutralize toxic vapors. It was out of service for maintenance. So, standards now mandate strict management of change and redundancy. You don't run a hazardous process if your scrubber is down. Second, the flare is the final line of defense to burn off escaping gas. On that night, a section of the piping connecting to the tank to the flare had been removed for repairs and was not replaced. This highlights the importance of isolation and blinding standard to prevent cross-contamination during maintenance. Point 3. The piping header allowed water from a routine pipe cleaning operation to leak through a faulty valve into the chemical tank because a blind flange, a simple standard piping component, was not installed. So this is a classic violation of double block and bleed safety principles. As a piping consultant, I always tell my students, codes are written in blood. So every line in the ASME or API books exists because someone somewhere did not use a blind flange or did not calculate the thermal expansion correctly or ignored material compatibility. When we follow codes, we are not just following rules, we are preventing the next Bhopal. Now take nuclear piping. The stakes are unimaginably higher. Codes like ASME BPVC Section 3 for rules for construction of nuclear facility components go to extreme length. They specify not just material and design but also detailed quality assurance program, traceability of every component, rigorous inspection, and exhaustive documentation. Why? Because even a tiny failure in a primary coolant loop could have devastating long-term consequences. So this is not just about preventing leaks. It is about ensuring containment, integrity under normal, offset, and emergency conditions. Moving on to our second pillar, legality. Codes and standards are not just good practices. Very often, they are legally binding. Governments and regulatory bodies frequently adopt these industry standards into their laws and regulations. This means that if your piping system does not comply, you are not just risking safety, you are breaking the law. So non-compliance can lead to severe penalties, hefty fines, project shutdowns, maybe loss of operating licenses, and even criminal charges in case of gross negligence or accidents. From a project perspective, non-compliant systems might not even get permits to operate. It might lead to massive delays and cost overrun. So imagine building an entire plant only to find out your piping system does not meet the local legal requirements because you did not follow the relevant codes. Consider a real-time example from a power plant. Power boilers and pressure vessels are typically governed by ASME BPVC Section 1 and 8 respectively. Regulatory bodies like OSHA in the US or similar organization globally mandate compliances with these codes. During routine inspection or recertification, inspectors will verify that the original construction adhered to the code and that ongoing maintenance and repairs are also compliant. So if a repair was done without following the correct welding procedures or using non-code compliant materials, the vessel could be deemed unsafe and taken out of service, halting plant operation and resulting in significant legal and financial repercussion. It is also crucial to remember that different countries and even different regions within a country might have specific jurisdictional requirements, often building open or modifying international codes. For instance, while ASME 31.1 for power piping is widely used, a European project might require compliance with EN 13480 for metallic industrial piping. So, as a piping designer or engineer, we must be aware of the specific legal framework governing our project location. Finally, let us talk about consistency and interoperability. Imagine if every engineer designed their piping systems based purely on their own judgment without any common guidelines. It would be utter chaos. Manufacturing components would be a nightmare and installing them even worse. So codes and standards provide a common language and a common set of rules for the entire industry. This consistency allows us for standardization of components. If let us have an example. A flange manufactured to ASME 16.5 will fit perfectly with a valve manufactured to the same standard, regardless of where or by whom they were made. So this predictability simplifies procurement, reduces manufacturing cost, and streamlines construction. It means engineers in different companies can collaborate effectively knowing they are all operating from the same baseline. Think about a global project. You might have pipes manufactured in India, valves from Germany, and fittings from the USA, all assembled on site in the Middle East. This global supply chain is only possible because everyone adheres to internationally recognized standards. Without them, every project would require bespoke components, driving cost through the roof and making replacement parts nearly impossible to source quickly during maintenance. Beyond physical components, codes ensure consistency in engineering practice. When I review a piping isometric from another design firm, I know that if it states ASME 31.3 construction, I can expect certain fundamental design principles to have been followed for stress analysis, material selection, and fabrication requirements. So this trust and common understanding are invaluable in complex engineering projects. So to recap, piping codes and standards are not just dusty old books. They are the bedrock of safe, legal and efficient piping design and operation. They protect lives, ensure environmental integrity, keep us on the right side of the law and allow our complex global industry to function seamlessly. As piping design engineers or designers, our commitment to understanding and applying these codes is paramount. So never view codes as restrictive. Always view them as powerful tools built on decades of collective experience and lessons learned, often from hard-won failures. They empower us to design with confidence and responsibility. That's it for day 8. I hope this deep dive into why codes and standards matter has been insightful. If you found this valuable, please hit that like button, share it with your fellow engineers and students, and subscribe if you have not already. What are your experiences with piping codes? Do you have a specific code you rely on heavily? Let me know in the comments below. And don't forget to check out our previous videos in the 90 days series. Join me for the next video for day 9 where we'll be discussing ASME V31 code family overview. Until then, happy designing.